Hello, everyone. I am Yan from the Seller Data, and today my session is about optimizing the query performance for Apache Iceberg at scale. So first, I will explain why we need a fast query engine for lakehouse, and then I will share some challenges and optimizations that we have done on query Iceberg table at scales. Finally, I will share a real-world use case. So first, why we need a fast query engine? The challenges with slow queries on lakehouse is because basically all existing lakehouse query engines are not built for the data warehouse workloads like high concurrencies, low latencies, and the customer-facing analytics. So as workaround, users are forced to copy data out of Iceberg and put data into the warehouse and move the workloads into a high-performance data warehouse just for the query acceleration. But by doing that, it just gives out all the benefit of lakehouse, right? Because the lakehouse hopes you just hold a single source of truth on the lakehouse on the Iceberg. So inevitably, you have to maintain multiple systems, which incurs to the high maintenance cost, and you have to manage data pipelines. And finally, you have to face the data governance issues. This is not what lakehouse expect, right? So that's why we need a fast query engine that can solve the problems on the lakehouse. So users don't need to force to copy data out of from the lakehouse. So what the fast query engine should be for the lakehouse? This is the architecture of data lakehouse, and from that architecture you can see first a query compute engine should be first efficient at processing the metadata from the catalog. Second, it should be efficient at parsing data from the table and the file format, like efficiently reading and decode the data from the Parquet files. Third, it should be also efficient at reading data from the storage, because as you know, if you put the data on the S3, the average latency could be 100 or 100 200 milliseconds. Yes, that's it's not tolerable for the customer-facing analytics. And finally, it should be also efficient at implementing all kinds of primitives operators like join, aggregation, sort, or window function, etc. It's quite hard. And there are some challenges of, besides that, there are some challenges of querying Iceberg table at scales. And just I want to list a few challenges just I came across from the real customer cases. Just a few challenges, not all. The first one is parsing the Iceberg metadata. Could it be the bottleneck? Could it be more expensive than everyone expected? And the second one is efficient way to handle delete files could be hard. Sometimes it's not an efficient way. And the third is that dispatching data and delete files could be in a blocking way. Okay, which I will come back to those challenges later while I presenting the solutions and our optimizations that we have done in the next few slides. Okay, since it's so critical to build a fast query engine, and there are so many challenges of build out faster engines, that's why we have a StarRocks. So I will give a little background of StarRocks. StarRocks is a distributed MPP query engine, and it uses vectorization techniques to parse data, to process data efficiently. And it has a cost-based optimizer to generate pretty good execution plan from the SQL. I won't say best, but pretty good. And third is that it has sort of killer feature, a materialized view for seamless query acceleration. So you will see that later. So the architecture of StarRocks is quite simple. There are only two rows in that, FE and BE node. So the FE node is a abbreviation of front end, which is to manage the metadata and query planning. And BE is backend to manage storage and query execution. So basically, you can think FE as a query planner, and BE as a query executioner, query executor. Okay. So StarRocks was initially designed for data warehouse workload, but since we are moving forward to the lakehouse, so the challenge is how to make data warehouse engine work well with lakehouse. Okay, here are the optimizations that we have done. Come back to the third challenges I have mentioned before. First one is metadata parsing could be expensive than you expected. Because usually the metadata parsing is done just in the query planner. It's like a single it's like a single node. So if think about it, if there are many manifest files are out there, so it should be take a very long time for the query planner to just parse and decoding those manifest files. So it could be the bottleneck. So what StarRocks do is StarRocks translates the metadata parsing job into a regular execution plan. It makes to a normal SQL, something like that. So every BEs in the systems can read and parse manifest files parallelly. By doing that, we can fully utilize the backend nodes and to avoid the BE to the bottleneck. While the latency could be reduced down to a fraction of number of BE nodes. So we fully utilize the resources. The second problem, the second challenge I mentioned is that handling position equality delete files could be inefficient because in traditional ways, deleted files could be read and parsed multiple times by different BEs, executor. And scan operators could have a very complex implementation inside. So what StarRocks is to, again, it translates the handling delete file job into a regular query execution. Like you can see from the diagram, we add, by using the left anti-join and the union all join nodes, how to do that. To handle the partition delete files, we add a left anti-join node with join predicate like on their file name plus position. And to handle the equality delete files, we add a left anti-join. The predicate on that is sequence number and the primary columns. And finally, we union date files without any delete files. That's it. So you can see it's just a regular sequels. Okay. So the result is that delete files are only read and parsed only once, and scan operators just have a simpler implementation. Meanwhile, we leverage the StarRocks efficient join algorithms. And the third challenge is that dispatching the files could be in a blocking way. So because dispatching files could be in a blocking way that BE, the backend executor, has to wait until the FE planner dispatch all files down to it. So before the FE collecting all files, the backend has to wait. All backends have to wait. It's a waste. It's a huge waste of resources. So what StarRocks do is the StarRocks dispatch file in small batch, like the FE after FE just collecting a small batch of files. FE just dispatched files down to the FE. So as a batch of files being dispatched to BE can execute instantly. But meanwhile, the FE can keep collecting the file, the data and the delete files. So you can see that the FE and the BEs can, work in a pipeline way. So the result is for some for common queries, the latency could be reduced down to 10 or 30%. But for some special query like previewing the data, like select star from T limit 10, the latency could be reduced more than 50% or even more. Yeah. So that is the general optimizations. We have some, besides that, we have some other features and optimization that could make the StarRocks be a better lakehouse engine. I just want to list a few. The first one is data and metadata cache. So we can save the I/O costs from the repeatedly fetching the data from the external storage, even that data has been fetched before. And the MPP memory data shuffling, it's just so the data exchanged between different nodes don't need be put on the disk like Hadoop does. It's way inefficient. And StarRocks is written in C++, so we can fully utilize the SIMD instruction set. And finally, I want to mention the materialized query rewrite. Because of that, customers can use materialized views seamlessly without manually changing any SQL at all. And you have to remember that the customer side usually have a very, very long, complicated SQLs. And after you want, and nobody want to change that, nobody want to touch that. And since we have materialized view query rewrite, just to create materialized views, boom, we just rewrite it. We just use the materialized views directly. No change to SQL at all. Yeah, so that's basically about StarRocks. So finally, I want to share a real-world use case. Here is the red node. It's also called Xiaohongshu. I guess it's probably you already know that because of recent events. Right, yes, okay. It's a social media company with 200 million plus monthly active users. Before they move the lakehouse workloads to the StarRocks, they already employ a real-time StarRocks cluster. And that cluster, there are 100 million rows ingest per day, and there are 30,000 CPU cores. Average latency could be down to 20 milliseconds. So StarRocks has a very good reputation inside the red node team, and they trust us. And once they want to move the lakehouse workload to other place instead of the Presto, they think about if we can move the workloads to the StarRocks. So they were using the Presto. The scale on the data to query the Iceberg and the Hive table. The scale of data on Iceberg table is EB level, and there are 10,000 tables. The challenge with Presto is that they have to maintain the StarRocks and the Presto. It's quite annoying, high maintenance. And they were not satisfied with the performance of Presto in terms of latency and concurrency, while they have a concern about high availability of Presto. And they replaced the Presto with StarRocks. And you see, StarRocks can directly query the Iceberg and Hive table. And if customers are not satisfied with the performance, okay, good, you create materialized views. Remember, we have a materialized views rewrite mechanism, so no need to change any SQL at all. Just query get performance get boost, transparently. So the result is that query sees average of 6 and 7 performance boost, P90%, decreased by 90%, and only have to maintain StarRocks, this stack. And the good thing is that since StarRocks can be compatible with the Presto and the Trino dialect, So the customer side don't need to change because they were using this Pretzel SQL. They don't need to change the SQL at all. So it they have a very, very fast migration process. So that's the case of Red Note. Okay, thank you. That's all. Thank you very much.
User of StarRocks at this point, but what was historically challenging for us is basically the Iceberg API does not provide you kind of good enough tools for like fetching updates, right? So unless new partition is created, you have no idea that old partitions were updated. So technically, when you referencing to the basically materialized view magic, right? So that is not a good suit for Iceberg unless you're doing append only and only appending the new partition. And basically there's a trade-off, right? So if you're caching metadata, then you have no way understanding what are the new things that were there. So what are you folks doing to solve that? Thank you. I'm sorry?
What's the problem? I don't catch up.
So, I mean, is there any improvements that you do on top of the Iceberg API that allows you to get updates faster? Because as I said, right, so unless Iceberg creates new partition, any AMVs that we create on top of that, they won't see that.
We create, you mean the materialized views? Materialized views, we create materialized views based on partition levels, refresh. That so if Iceberg partitions is updated, we have to materialize this partition materialized views has to be refreshed to caught up.
So you're saying that like the mapping of AMV partitions to Iceberg partitions would actually watch the partition update?
Yeah, yeah.
And like if it's a merge and read, it also watches it at this point?
Yes, partition levels catch up.
Okay, so but that won't work with metadata caching?
What kind of caching? Sorry.
So you mentioned basically that
Metadata
you're
caching.
unpacking Avro manifests and so on, right? So, and the way to streamline and improve that, you folks are putting caching into it, right? So basically, if you cache it, then technically you won't be able to.
We cache the manifest file instead of when we pass the metadata, we just cache the manifest files to avoid to
Yeah, but I mean, like, boom, I created another snapshot and another manifest files are in. So what to do in this case?
Yeah. Yes. We will. Yeah. Yeah.
So basically, and this is done by like monitoring Iceberg snapshots?
Yes, background. Yeah.
Okay.
We have a background process to do the partition refresher to keep comparing what is the latest what is the latest snapshot of a partition update time compared with our materialized views update time.
Okay, I see. Yeah, that might work. Let me test it, and I'm gonna back to your GitHub. Thank you.
Okay.
I also like the Kingbox stance that basically it's a relatively near model that allows you to reconstruct the chain line on command. You can actually, I mean, in Iceberg, even pages represent leading insert, so by default you would look at bigger domain with time limit or quick snapshot, and then you get the contact. And in Spark, there's a way where you can reconstruct the three box thing. Right now, it's only on the primary key, but there's no need that sudden name tree. That would allow you to reliable reconstruction of the chain box. You can actually query with the changer and see what actually changed in particular time limits on that page. That's essentially the mechanism that you can use to then either grab or like notify public.
Yeah, I see. I mean, like just for my in-house product, right? I want to rely on the tooling that I use, which is StarRocks in this case. So I'm sort of waiting patiently until this can be pulled in. Otherwise, like AMVs on top of Iceberg been, let's say, problematic. As usual, trade-offs, 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 right? So either you're pulling, updating, or you're giving this blazingly fast performance of AMVs on top of Iceberg, say. Thank you.
How many QPS can each vCPU handle with StarRocks? Yeah. What is the max performance you've seen?
I don't know if it totally depends on your customer scenarios, right?
Like on an average, what? I'm just curious to see like the concurrency.
Average QPS.
Sorry?
Average, you mean average QPS?
Yeah.
I don't know, maybe for simpler for simpler point queries, like you can, well, like 100 or 100 nodes, you can probably sustain to 100,000, 10,000 maybe QPS, I guess. We have those customers, but if you have a very complex queries, then QPS won't be not high. It totally depends.
Okay.
I won't say
Depends on the
exact number.
queries, is what you're trying to say.
Yeah.
Okay.
Okay.
Thank you.
Okay. So did you implement Iceberg in C++, the spec?
No.
You use Java?
We use we kind of read the bucket files in C++, but we kind of doing the metadata parsing sort of stuff at FE using the Java, using this C++ or Iceberg Java SDK, but we don't use. No, we don't use the JVM. But okay, for the query, actually query the data, we use the C++ to the parse the packet files directly. But for I've mentioned there's a distributed metadata parsing, because that parsing could be very complicated. So we use the Java JNI to call the Java at that part. But for the normal queries, we don't we directly parse in the packet files in C++. Yeah.
I see. When you do distributed planning, and then how do you pack manifest so that you utilize the compute as much as possible?
Yeah.
Because what would happen is that in one manifest, you end up scanning only one file, but on the other, you end up scanning 2 or 3 files. How do you efficiently bin pack before distributing those manifests?
Yes, we have kind of auto mechanism to decide if this manifest files is large enough to be distributed, but it's quite detailed. It's written by, okay, actually it's written by another guy. Yeah.
Okay.
There is a heuristic, yeah.